Alright, kiddos, here goes the renewable energy notes. In the interest of making these notes a little shorter for YouTube, I'm going to try and minimize what I say for each slide. Just keep in mind if it's not enough time for you to write it down or not enough time for you to read what's actually written on the slide, you can always pause the video and do so. I know that'll take just a smidge more time, or actually probably a lot more time, but come on guys, it's your AP test you're studying for here. And learning for. I'm sure as an environmentalist I'm rather biased, but renewable energy has a list of advantages over non-renewable. Hopefully, little to no environmental impact in the long run. They can be expensive to put in place, but once you have them established, they hopefully will not need a lot of input of energy to keep them running. And, I mean, it can be scaled up or scaled down as needed. That applies to non-renewable sources as well. But hopefully the idea is behind renewable energy, you can have limitless energy being produced. As I wish they were, renewable energy resources are not the fantastic magical cure for our energy problems. There are large setup costs involved. For example, if you want to install a wind turbine or if you, say, wanted to install solar panels on your own home, it costs a lot in the short term, so it's very expensive to put into place. There is the possibility of environmental damage in the short term, and there's a limit to the efficiency of these systems, although hopefully with improved technology that can be overcome. And then renewable energy resources aren't this kind of cure-all for our energy needs. You can't just say, okay, everything's going to be good if we just use solar, or everything's going to be solved by using wind power for everything. Each region is going to have to use renewable resources based on what it has available in the area. For example, you wouldn't want to use solar power in a place like Seattle that doesn't get a ton of sunlight, and you wouldn't want to use hydroelectric power in a desert area with no rivers. So it has to be tailored to the local area. Talk about several different types of renewable energy as we go through this lesson. Of course, we're going to talk about the big three, which is solar, wind, hydroelectric. We'll also talk about a couple of technologies that are a little more experimental, like wave and tidal power as well. Let's start with my personal favorite for the state of Texas, solar energy. If you ask most people what is solar power, they'll point out solar panels or solar cells, kind of like the ones you have on the simpler calculators. But the truth is there are lots of different ways to use solar power. There's active solar power and there's passive solar power. Passive is the easiest one to use, probably the cheapest one to do. It tends to happen when you're designing buildings that you'll figure in passive solar power. So you'll make sure that windows are faced in such a way that they'll receive maximum sunlight, especially during the winter when you want to warm your house. Or you can use active solar power, for example, if you want to get a solar powered water heater, which will heat up your house without using, heat up your water without using electricity. Here we see passive solar design. So the house is designed so that during the summer, with the angle of the sunlight coming in, it's not going to hit your windows, so you won't have extra heat in the house. However, when the angle of sunlight coming in is shallower in the winter, you'll get some sunlight entering the house and help heat it up. And this requires, of course, no extra energy, no moving parts, and no expensive solar panels either. On the other hand is an active solar collector. So while it looks kind of like it has a solar panel in place, that's actually just a panel that absorbs heat from the sunlight, and that heats some water so that you can have a water heater basically heated by solar energy. There is a pump necessary to move the water around, and because it's actively using energy, that's why it's an active solar collector. In fact, these things are supposed to be pretty efficient and pretty money and energy saving because one of the major expenses that you have in a house tends to be heating water for the water heater. So someday I hope to get one for my house too. So here is what most people think of when they think of solar power. A solar panel, otherwise known as a photovoltaic cell. Keep in mind the photo in there means that it's activated by light. That's why you need the sunlight. The voltaic part refers to the electricity that's being produced. So how does one of these work? Well, you have to have a special material called a semiconductor, and you have a layer of that in the photovoltaic cell. When it gets hit by sunlight, what happens is that an electron will get excited, kind of in the same way one gets excited during photosynthesis, in the chlorophyll and the pigment in a plant. In this same way, an electron will get excited after being hit by sunlight and absorbing the energy from it. It'll leave the electron, and then there's a positive charge that the electron gets attracted to. As the electron's moving towards this positive charge, it gets shunted into a wire, and that flow of electrons that you have is electricity. By the way, this is what Albert Einstein got his Nobel Prize for. He got it for developing the photovoltaic cell, not for developing the theory of relativity or his E=mc² equation, like a lot of people tend to think. Contrary to what you might imagine, when you have a solar power station, it's actually not a ton of solar panels all lined up. Solar panels tend to be pretty expensive, so you don't want to just build a huge array of them. What's actually cheaper is to build something that has mirrors that focus the heat or the light of the sun. That warms up something, and then that substance that's warmed up, either it can be used to have fluid heated or to produce steam, and that'll turn a turbine just like you have in traditional electric generating power plants. And so that's how most solar power stations are going to work. Different solar power stations operate by different methods, though. You've got the central receiver system where you have mirrors. They're going to focus all the light on one central tower, and that's where you're going to have water or, in some cases, molten salts, which need very high temperatures to melt, where you're going to have that heated up by this combined heat. And then after that, it's just going to be traditional electricity generation. A distributed receiver system, on the other hand, is not going to use this kind of central tower. What will happen is you'll have these mirrors. They're curved mirrors, and so they'll concentrate the light coming in at a certain point, a certain distance from the mirror. At that point, you've got an oil-containing pipe. It's going to contain material that you'll heat up with all that focused light, and then you can use that to heat water to turn a turbine. Like I said, different methods of collecting the solar energy, but in the end, the method of electricity generation tends to be pretty much the same. These parabolic dishes with Stirling engines are a little more complicated. So what's going to happen is these parabolic dishes do focus light, kind of the same way the mirrors do in the other two types of solar power stations, but they're going to focus it on a Stirling engine. That's going to heat a chamber up, which is going to basically drive an engine that's going to produce electricity. I'd give you more details, but I don't think they're necessary for the test. If you're interested, you can always look this up independently. Ocean thermal power is kind of a subset of solar power just because it relies on the fact that you've got temperature differences between deep water and surface water, and that's ultimately caused by the sun. You can use that to produce electricity, but it's really only useful in tropical areas, and it doesn't give you a lot of energy, so it's going to have low net energy yield. So it's probably not going to ever be a very widespread technology. Solar pond is another type of technology. Basically what you're doing is you're getting the solar energy to heat up some water. The way you keep traditional convection currents from forming and allowing some of that heat to escape into the air is you create a saline gradient, which kind of disrupts the currents that could flow. And so what you then do is you just basically have this light absorbing material in the liner of the pond. It absorbs a lot of energy, and that heats up water. That water can then be used to heat up other water to create steam, and that turns a turbine. So, variation on the same theme. This is just a close-up of the heat exchanger from the solar pond. So, the water that's heated in the pond never actually physically comes into contact with the turbine. It's used to heat other water, so you're transferring the energy from some water to other water. And it may not seem extremely efficient, but this tends to be how a lot of power plants work. They don't directly heat whatever's turning the turbine. They heat some water or some oil or some salt solutions that end up transferring their heat to the water that's turned into steam. Okay, for each of the renewable resources, I'll have one of these summary slides. So if worse comes to worse and you can't sit through the whole video, at least go to these summary slides and get the gist of what the major concerns are and the major advantages are of each renewable resource. Just a summary of the advantages and disadvantages of solar power. While it can theoretically provide a limitless supply, especially in areas where you have a lot of sunlight, that's obviously going to not be efficient where you have limited sunlight or you don't have a lot of sunlight certain parts of the year. There's a relatively high gain of energy, and it does reduce reliance on foreign oil. That's an advantage of all the renewable energy resources. It doesn't produce a ton of pollution just in making the solar panels or the collectors, and that's the major source of environmental impact. Another drawback is that you're not a drawback, on the other hand, is going to be that this can only produce energy during the daytime. However, you can develop what are the equivalent of giant batteries that can store this energy so that it can be used at night. Unfortunately, when you've got a solar power plant, that's going to need a lot of land, and it'll shade the land underneath it or disturb it, so you're going to disrupt the natural ecosystems. There is a high maintenance cost, and that is especially a factor when your systems break down and you've got to replace stuff. And the current efficiency is about 10 to 25%, and that's not something that's likely to change in the near future. You can tell from the image, we're moving on to wind power. Globally, as of the time when these images were produced, which is probably about 2007-2008, wind power produced about 1.5% of the world's needs for electricity. However, it's not being utilized as much as it could be. For example, some estimates have said that wind power could generate most of the electricity needs of the United States from just a couple of regions having wind farms. You can see there are different numbers. We do produce more wind energy than a lot of other countries, most of them, with the exception of Germany. But you've got to keep in mind, we also have a lot higher energy demand that we use. So we probably don't get as high a percentage of our energy from wind power. Said on the previous slide, wind power has the potential to generate a lot of electricity. In fact, if you used wind farms in the Dakotas, north and south, and in Texas, you could provide electricity needs for the entire United States. And this is just showing you who produces wind power and how much in Europe. What's going to become a common theme is Germany is very big on using renewable energy. So you'll probably have more renewable energy produced in Germany than any other country. That's probably going to hold the same for all of these sources of power generation that are renewable. A couple of general facts about wind energy. If you want to have a completely efficient wind turbine, you're going to have relatively constant speeds, around 20 kilometers per hour. There are some locations, obviously, that are better than others for wind farms. Tops of ridges, basically kind of like mountain ranges and such, coastal areas, and anywhere there's wide open plains. The average turbine will produce anywhere between 40 and 400 kilowatts of power. This obviously depends on the size of the turbine. If you have a couple of factors affect the amount of electricity that's going to be produced. For example, if you have a very tall wind turbine, that's going to catch faster air currents and produce more electricity. And then if you increase the length of the blades, that's going to increase the electricity that's produced. In fact, if you double the length of the blades, you're going to get a 4 times increase, or a 400% increase in the amount of power that's produced. And wind speed is variable. You can have gusts of high wind. So to do that, you can feather or turn the direction of the blades so that they won't be spun during periods of very high wind, such as hurricanes or tornadoes or storms, and that'll help prevent damage to the turbines. Wind turbines do use the movement of a fluid to turn a generator, but they're not using steam, they're using the movement of the air itself. Remember, air is a fluid as well, it moves. And so what happens is when the blades are turned, this is ultimately going to drive magnets inside wire coils, and that's going to produce electricity. You see a gearbox there. That makes sure that you, despite the fact that the wind speed may vary, you'll have a constant speed in the drive shaft, which is turning the magnets inside the generator. You'll also have several gears in there, which will make sure that they'll basically amplify the movement of the turbines. If you see wind turbines turning when you pass a wind farm, you're going to see that they don't spin very fast, but gears inside of the gearbox are going to make that rotation kind of faster for the inside the generator. That was our extremely brief presentation on wind energy. Some pros and cons. You can build wind farms relatively quickly, and a cool thing, you can even build them on sea platforms, so you can build them offshore. Once you get them built, maintenance is low, and it can be automated, so you don't have to have a person going out and maintaining these wind farms. You get pretty decent net energy yield, and it's not going to produce pollution. A lot of times these are located in remote areas, so it won't bother people. And if you have these large turbines, you can use the land underneath for agriculture, for raising animals, etc. Some of the drawbacks: you do require an area with steady wind, which minimizes the locations where you can use this. You do have to have some backup systems in place when you don't have time with wind. People consider them noise pollution, visual pollution, meaning that they interfere with the pretty view. And there is talk of noise pollution, although I have spoken with people who have been directly under wind turbines and say there's no noise produced. A big problem with wind turbines is that they can actually end up causing death of birds, bats, anything that flies in the air, because the animals don't see the turbines and they end up hitting them and dying. Major ways to avoid this unnecessary death of wildlife is to research before you put a wind farm in place, and make sure that you're not placing these wind farms in major migration patterns. Birds tend to use the same route when they're migrating every year, so if you know thousands and thousands of birds are passing through an area, don't put a wind turbine there. Another thing is wind turbines may interfere with certain signals like TV and cell phones and microwaves. I don't think that's microwave ovens particularly. Hydroelectric power is one of the most widely used renewable power resources that you'll find throughout the world. Notice this diagram is a little different from the one showing wind power. Instead of listing percentage of wind power by country, it's showing the 10 largest hydroelectric dams and the amount of electricity they produce. And as a whole, hydroelectric power produces about 19% of the world's total energy supply. I'm going to point out specifically the Three Gorges Dam, which is in China. Notice it produces 22,500 million megawatts, and it is the largest hydroelectric dam ever built. We'll talk more about it when we talk about land and water resources, because there's obviously been some environmental consequences from building that dam. Here in North America, we have a number of dams that produce electricity. The one that produces the most is the Grand Coulee Dam, which is up in the Pacific Northwest. The Hoover Dam is particularly famous. It's on the Colorado River. And there's actually a number of dams on the Colorado River, which we'll talk more about when we talk about land and water management. Then you also have hydroelectric dams in Europe. You've got to keep in mind, notice I said that the country of Germany uses a lot of renewable energy, but the thing with hydroelectric power, you gotta have a river in place. So apparently Germany doesn't have any rivers that are very easy for it to dam up. Hydroelectric power is all about the potential energy behind water. When water has to go over a height, over a cliff, something like that, the potential energy of that water before it goes over the cliff can be pretty high. So what happens is, for a dam, what you're doing is you are blocking up a river, you're building up a reservoir, and there's a lot of potential energy stored in the water in that reservoir, which, being pulled down by gravity, would, if unimpeded, flow down whatever obstruction you have. When that water is allowed to flow, it's driven through pipes, and those pipes go through a powerhouse where the water turns a turbine, and that is connected to a generator that then produces electricity. Basically, the further the distance the water has to go, and the more the water that you have, the larger the amount of electricity you'll be able to produce. So here you see a hydroelectric dam. The water is going to be flowing from the right to the left. So you see the reservoir on the right-hand side. You see the water flowing down. It's going to turn a turbine, and then it'll end up flowing further down river. Notice you see the powerhouse, you see the generator, and all of that. Now we get to the pros and cons of using hydroelectric power. One of the pros is you can actually control the flow of the water downstream. So let's say there's flooding upstream of a dam, you can catch that extra water in the reservoir, and that will prevent flooding downstream. Once you get it built, the cost to operate it and maintain it aren't very high. You're not going to produce any pollution from producing the electricity, and dams can last for a long time. They also give pretty good net energy yield, and when they create lakes, that's going to create areas of water recreation. In fact, in North Texas, we have about one naturally occurring lake. So all of the lakes you may go to, Joe Pool Lake, whatever other lakes there are, all of those are man-made by damming up the Trinity. There are, however, a lot of negative consequences of dams. It creates a large flooded area upstream of the dam, and if there were people living there before, they're going to be forced to move. When you have water that's approaching a dam, its pace is going to slow down. And so when you have slower moving water, you can have pathogens like mosquitoes there. When you flood an area behind a dam to build a reservoir, that's going to destroy any wildlife habitats that are in that area. And the problem is fish don't really mix very well with dams, and especially if you have fish that swim upstream like salmon, and that's going to affect fish migration. Another thing that you don't tend to think of, but is a really big problem with dams, is that the slower water is moving, the less sediment it can hold in it. That's why traditionally when water in a river is approaching the mouth of the river, it's going to drop its sediment load. When you have a reservoir interrupting the flow of the water in a dam, in a river, what's going to happen is when it reaches the reservoir, the water drops its sediment load because it's not moving very fast. That means you're going to have a bunch of sediment build up in the reservoir, and after that sediment build up, you're going to have to dredge or take out some of the bottom sediment layers of the reservoir. Otherwise, it starts to fill in. Another thing is when those sediments get dropped in the reservoir, they don't reach downstream. Now, traditionally, rivers, floodplains, the areas where it's kind of the plain that's approaching the mouth of the river where it reaches the ocean, those areas are flooded regularly, sediments are dropped there by the rivers, and that's why they're so fertile. That's why a lot of farmland, a lot of agriculture has taken place along the banks of rivers. Those sediments don't reach downstream when you have a reservoir in place. Dams can also be expensive to build, and when you put them in place, they're going to destroy the character of a wild river. The thing is, when you have a lot of water held behind something made of concrete, any sort of small crack or anything like that is going to allow all that water to come out and flood downstream. When you have an earthquake, that can create cracks in a dam, and that can cause catastrophic flooding downstream. Another thing is that when you have that stagnant water in a reservoir, it's not going to be getting any dissolved oxygen, and so you'll have anaerobic or without oxygen respiration, which will lead to methane being produced, and that's released from the reservoir. We finally move on to geothermal energy, which, as you guys know from the presentations in class, energy from the earth. Now, since geothermal power is going to be using basically the heat from the interior of the Earth, it's only going to be possible in places where that heat rises close to the surface. So in areas where the Earth's crust is thin or areas of tectonic activity. What you do is you use that heat to heat water, and you'll get a couple of different things. You can get dry steam, which means you don't have a lot of water droplets. It's all going to be gaseous water, and that can be used to turn a turbine immediately. Wet steam, you have to take out the water droplets before you can use it to turn a turbine. And when you just get hot water, that's used to basically heat homes or heat businesses um, rather than produce electricity. Geothermal energy doesn't tend to produce a ton of electricity throughout the world or the United States. There are some countries like El Salvador, Kenya, the Philippines, Iceland, and Costa Rica which generate more than 15% of their electricity using geothermal sources. Map shows you those shaded in areas are areas where it's easy to use geothermal energy. What you should recognize from this, hopefully, is the fact that a lot of these easy to use geothermal energy spots are places where there's a lot of tectonic activity. Notice the Circum-Pacific Ring of Fire is especially an area where you can use geothermal energy. This is obviously areas where you've got heat from the Earth's core, from the mantle, coming closer to the surface. So there are limits to where you can use geothermal energy, which is one reason why it'll probably never be a huge producer of electricity for the whole planet. This is basically the process of getting geothermal energy. You can get underground steam that's already being basically produced. You can pump water into the ground so that it gets heated up. That's going to come back up, go to a power plant, turn a turbine, and you get electricity. You can also then recondense that steam and pump it back into the ground, so that way you can just keep reusing the same water over and over. This is just another kind of more complicated view of the same thing. If you really want, you can pause it and look at all the steps. I'm not going to waste our time talking about it again. Alright, so let's summarize geothermal power. You do get pretty good net energy yield from it, and it does have some high efficiency. Another thing is you can also have this resource be used indefinitely if you manage it properly. And it doesn't produce air pollution or carbon dioxide, which is a big plus. Also, in areas where geothermal energy is usable, the cost is competitive when compared to fossil fuels. Unfortunately, there are a number of downsides. Like I said before a couple of slides ago, you can't use geothermal energy everywhere. And if you don't manage it properly, you will deplete the resource and you won't be able to use it again. There's also some noise, there's some odor pollution that's caused by it. Basically, it smells bad. If you're extracting water, that can cause subsidence, meaning sinkholes and sinking of the ground. Here's a big thing. It can increase tectonic activity. You're already doing this in an area that, in general, is prone to tectonic activity. What can happen when you start drilling and putting pipes into place is that you can cause earthquakes. There was one site in Germany where they were trying to put a geothermal power plant, and when they were doing the drilling, they had a series of 1,000 small earthquakes in a short period of time, at which point they decided, yeah, it's probably best not to drill in this area, let's leave it alone. Another thing is you're letting stuff from deep underground come up to the surface. That can produce saline waste, some corrosive chemicals are released, and it also produces some thermal pollution as well. We're going to move on to what plants can do from us. As you can see from this clever little picture, biofuels are when you're going to turn plant matter into fuel, particularly for cars. So biofuels are made from fermenting plant matter. It's actually basically the same process that's used to make alcohol. And what is produced when you're making biofuels is ethanol. Not drinkable ethanol, so please don't go to a gas station and start trying to drink from the pump. Mostly it's not used on its own, it's used as an additive to gasoline to kind of help extend it and basically make our gasoline supplies last a little longer. The two countries where it's used the most is our country, and then Brazil uses it a lot too. It's the source of about 1.8% of all the world's transport fuel. This is biofuels, there's bioethanol, there's biogas, biodiesel, and green diesel are the different types. Several different sources for biofuels. Traditionally in the United States we use corn. In Brazil they use sugarcane. Although there are movements to try and find ways to use other sources. For example, when you harvest plants, a lot of times they pull up the entire plant, but we only use a small part of it. The thought is to try and use some of that plant waste as a source of fuel for biofuels. There's also the thought to try and use switchgrass, which is a type of grass that kind of grows as a weed. And if you could use that, you could use land that's not devoted to agriculture, and therefore you wouldn't be competing with basically food resources being produced on that same land. Another source that you can use is you can dry out animal dung, which is animal poo, and you basically leave it out in the sun, let it dry up, and then you can burn it later as a fuel source. Yeah, don't get too grossed out. That's done in a lot of parts of the world. Another way that you can use your poo is basically sticking it in a fermenter or in a digester where you let bacteria do their duty. I made a pun. And they're going to break this stuff down. Mostly what you want to get them to produce is methane, and that methane is biogas that can be then burned for fuel. That's renewable because, there's a never-ending supply of poo on the planet. This is a lovely diagram showing you how biofuels are renewable, basically because whatever carbon dioxide you are releasing into the air from burning biofuels should be taken up by the new plants that you're going to plant and harvest to make new biofuel. So theoretically, everything you're putting in the air is stuff that you're going to take out of the air by growing new plants, which makes it a carbon neutral source of energy. Okay, so the pros and cons of biofuels. When you use it sustainably, and when you make sure that the biofuel that you're burning is balanced out with the rate at which you're planting new plants to take up that carbon dioxide, it's renewable and it's not going to disrupt CO2. When you burn it, it's going to produce less other air pollutants than fossil fuels, so it's not going to produce sulfur-containing or nitrogen-containing compounds. And if you can do this with plants that are not food plants like sugarcane or corn, then you can plant in areas that you don't really want to use for agriculture, and you can use it to reduce soil erosion. And you can also use this to create jobs as well in rural areas. Now for the cons. It does require water and fertilizer so you can grow these plants. And as we'll talk about in a couple of weeks, when you use a lot of inorganic fertilizers, when you use herbicides or pesticides, things to kill unwanted weeds or insects, then that can cause environmental damage. Another thing, this can cause deforestation. For example, in Brazil, where they use sugarcane, they'll often cut down chunks of rainforest so that they can find a place to plant their sugarcane so that they can make biofuels. That is obviously a bad thing. If you don't burn this efficiently, like for example in the proper engine, it can cause air pollution, which means that, of course, you have to have a car that's designed to run at least on a biofuel or a biofuel mix. One of the biggest concerns is that a lot of land that was previously used to grow food for people is now being used to grow food for biofuels. And so when we have a growing population, limited land for agriculture, what are you going to grow the food for? Are you going to grow it for people or are you going to grow it for cars? All right, biomass is another way of using living matter to produce energy. A lot of times what happens is you're going to burn the biomass. So common biomass fuel that's burned for energy is going to be wood. I mean, hey, it's what people used to use for energy before they discovered coal. You can also use biomass to make plastic products. More and more now, especially if you look on, for example, a Dasani water bottle, you'll see that it says it's a plant bottle. It's made from plastics that are produced from plants. This does supply a small amount of United States energy. I'm not talking about wood burning. I'm talking about burning other biomass. And if you grow plants for this that have really extensive, really deep, really complicated root systems, that can actually take some carbon out of the atmosphere and stick it in the soil. So on to the pros and cons. What you can do is you can use parts of plants that you wouldn't use otherwise. So that is a useful thing. Sources that I've read have said that you can collect and recycle the ash. I'm not sure how you recycle ash, though I do believe you can use it for concrete and stuff. And it'll reduce the impact on landfills because if you're just throwing away the unused parts of a crop plant, then that'll end up in a landfill somewhere. The net energy isn't too great, which is one of the cons. You got to use Part of that is because you've got to use energy to dry this stuff and transport it to a central facility, because if you don't burn it in a central facility, that can cause some bad air pollution. Um, and it also produces CO2 as well. We're also trying to use ocean waves and tides to produce electricity as well. Sorry for the delay there. One of my cats was twitching. This form of tidal energy that I'm showing you actually results in kind of blocking off an area where you have water coming in. Notice you kind of have this narrow area through which you're forcing water to go through, and as it goes through, it's going to turn a turbine. It's mostly going to be effective in areas where you have kind of a narrow area where water's trying to get through. Or water's constricted by a landmass, so a bay, the mouths of rivers, etc. It's not a fully operational technology yet, so there's not a lot of commercial scale production. In 2 slides, I'm going to be showing you some more experimental ideas that haven't actually been put into production or use. So this is an idea or a concept that some people have had where you basically have these turbines out in the water. And as the water moves past, you of course put this near land where you'd have tides coming in and out, and that would produce electricity because the water would turn the turbines. There are concerns about marine life getting killed by this, though, or it interfering with boats and ships that are trying to move through these areas. Similar system, although it looks like it's kind of more in deeper areas, and it does look like it kind of takes up maybe a little less space so that it wouldn't get hit by fish or other creatures as much, but it's still got the same principle of a turbine that's turned by the movement of the water. This is one of the experimental technologies I found particularly cool. This is wave power. So you're using the movement of water as waves go in the ocean to produce electricity. Unfortunately, it's kind of a difficult thing to put in place, so it's probably not going to be lacing the surface of the oceans anytime soon, but it's still a really neat idea, I think. So here's a few more details on wave power. There's not really widespread commercial production of this, although there is one commercial wave farm off the coast of Portugal. There are a couple of different designs that you can use to produce electricity. We'll talk about 2 of them on the next couple of slides, but there are limitations with anything in the ocean. It's pretty expensive, and you also have the problem that salt water will eat up machinery. So you're going to have a regular replacement, or you're going to have to try and find something that salt water will not eat through, which is very difficult. Also, it's got to be able to withstand waves that are produced by large storms without getting too damaged. So here we have some really neat wave tubes produced by the Palamas Corporation, I believe. And what happens is they have these long sets of these tubes just kind of laid across the ocean. They are, of course, anchored in place. You don't want them to float away. And what happens is as the waves move, they'll bend these tubes because they're not long solid tubes. They're connected by these hinged areas. When those hinges are bent, that's actually going to move hydraulic fluid, and that's going to turn a turbine and a generator, and that's going to produce electricity. So the movement of the waves is going to actually produce the electricity. Another idea that I find particularly neat, although I don't think it's anywhere near a stage of production, where you basically have these large buoys. Now, they don't look very large here in this picture, but in reality, they would be about 12 feet tall, which is 2 times some of the tallest people that you can find at sunset in height. You have this magnetic shaft on the inside that's anchored to the seafloor, so it's not going to move. But the outer casing and the electric coil that's connected to it, that can bob up and down based on the height of the water or the surface of the water. So as a wave comes through, that outer casing and the electric coil is going to move up and down. So when you have magnets moving through an electric coil, that's going to produce electricity. I thought that's a pretty neat idea, so I demand one of y'all go out and build it. Y'all have $1 million, right? Now we come down to hydrogen fuel cells, the dream of many a car maker. Or what you would think after you watch Who Killed the Electric Car. One of the big things about hydrogen fuel cells is that you've got to find some way to produce the hydrogen first. Yes, hydrogen is the most common element in the universe actually, but it's kind of hard to purify it out from air. So the most common way to produce hydrogen is to take water and to split it into oxygen and hydrogen. Unfortunately, that takes a lot of energy. And when you do that, I mean, you're putting in a large energy investment to split the water apart. By the way, my apologies for the typo in the title of this slide. It's supposed to say electrolysis at the end, not electrolysis. So there's an is at the end of that. Okay, bear with me, guys. This is a, quote, simplified model of a hydrogen fuel cell, but it gets a little dicey. All right, so you have hydrogen molecules, and as they move through this fuel cell, they're going to have electrons removed when they react with a platinum catalyst. They're going to pass through this catalyst, and then they're going to react with oxygen gas that you also pumped in, and with any of these removed electrons. And that's going to form water as your waste product. But the electrons are not allowed to pass through the same path as the hydrogen gas, so they're routed through a circuit, through a wire, and that movement of electrons creates electricity. Now, the technology is still developing. When I got these slides that I use for a lot of the PowerPoints, it said that it was expected in the marketplace by 2010, but we're in 2014 and we don't really see it yet. So there are obviously a lot of problems with hydrogen fuel cells as a power source. To the pros and cons of hydrogen fuel cells. So, one of the biggest pros and one of the biggest attractions is that the only waste product it produces is water, which is great. We need water. You can also use salt water for electrolysis, which is great because if it was only fresh water that was being used, we'd have a problem. We've got limited freshwater supplies. So that part's going to produce not too much of an environmental impact. You can also transport hydrogen through pipelines, and supposedly you can store it in compounds to make it safe to handle. Although if we look at the cons, there's the fact that on the last point it says currently difficult to store hydrogen for use in automobiles, which is the biggest intended use of it. Another big con is it takes a lot of energy to produce hydrogen from water or from methane, which means that you're going to have a lower net energy yield because of that. And then to change all of our infrastructure, which is currently devoted to basically transporting and using gasoline, to change that over to hydrogen would be very expensive. Here's a summary of some of the different methods of electricity generation. Notice it's got renewable and non-renewable sources as well, kind of to cap off the whole energy topic. I'll let you guys pause this if you want to look at it. I'm not going to go over each and every part of this though. I hope you've taken away one thing from this lesson. And that is that there's no cure-all for our energy problems. So one of the things that we're going to have to focus on more in the future is conserving energy so that we need less of it in the first place. So obviously the first stuff in this slide says, yeah, we have limited energy resources as far as fossil fuels go, and as far as renewable energy isn't perfect. There are a lot of pros and cons to each source. So it's important not to waste energy. So a couple of things we'll focus on is making a household more energy efficient. We'll talk about hybrid vehicles and then some of the future energy solutions that are possible. What this graph is showing is there's a lot of energy that's used to heat a home, especially this past winter when it's been really cold. One of the least efficient ways, only gives you about 25% efficiency, is electrical resistance heating, which is the standard type of heating most of us probably have in our homes. If we use, or if we look at the bottom of the graph, you see super insulated home, meaning it's so insulated it's not losing very much heat at all. That's got close to 100% efficiency. That's probably difficult to do unless you're designing your home from scratch, as is passive solar. But if it's possible to change over from like coal power electrical resistance heating, which you see at the top, to hydropower electrical resistance heating or natural gas heating, that's a little more efficient than just, coal power electrical heating. Other big thing is what you use to light your home. A good thing is in the past few years, it's become a lot more common to use those compact fluorescent light bulbs, or the swirly ones, as some of y'all call them, like what you see at the top. Those turn a lot more of the electricity that they get into light, as opposed to the old school incandescent light bulbs. If you've ever experienced those, when you try and change one of those, they're very, very hot when they've been turned on for a while. And the reason is a lot of the heat, a lot of the electricity that's going into that is not producing light, it's producing heat instead, which is a waste. You can use heat pumps also to heat your home, which is going to produce more heat for the same amount of electricity. And then solar water heaters will also kind of basically help reduce electricity use because one of the larger costs in a home as far as electricity goes is heating water in the water heater. Let's look at this energy efficient home. We're going to move through it starting with the top left hand side, and we're going to go counterclockwise, meaning the opposite direction a clock runs. So if you use energy efficient light bulbs, that's going to reduce your electricity use because you're getting more light generated. They also tend to last longer. You can use a heat pump. You can also connect that to solar heating so that you can heat your house. Energy efficient light appliances use less energy. In the United States, you can see they'll have an Energy Star label on them that proclaims that they use less electricity. You can have underfloor insulation. You can have water pumps that pump, basically, they're heated in the attic or they're heated in the ceiling. And then you can use that to redistribute heat to underneath the floor. Heat rises. If you have your building built in the right way, it can allow for passive warming, passive cooling. When you have double glazed windows, that's going to reduce the heat that's lost through your windows. And then, of course, at the top, you got solar panels to produce extra electricity for heating, lighting, cooking, and other things that you need. So, hybrid vehicles have become a much bigger trend in the past few years. I know we've watched Who Killed the Electric Car in class. Hybrid vehicles are kind of a, I guess, stopgap measure in between getting fully electric vehicles. They have a gasoline engine, but they also have an electric engine, so an electric motor, which is going to provide the energy for a lot of the time when you are driving the car. You're mostly going to use your like a gasoline engine when you're accelerating, when you need a little extra power. So that does improve fuel efficiency dramatically, but you still do need gasoline to power it. Number of different hybrid vehicles available, the most famous of which is probably the Toyota Prius, although Honda and even now a lot of American car companies are starting to build hybrids as well. Hybrid SUVs are also in production as well too. Forgive the measurements on this slide. This slide came from a company that's in New Zealand where they use the metric system, unlike us. A lot of the energy use in the world is used for transport, and a lot of that ends up not being efficiently used because internal combustion engines, the type we use to drive cars, they produce a lot of heat and they produce a lot of sound, which is wasted energy. Ideally, the best thing to do would be to use public transport. Unfortunately, that's not always an option, especially here basically in Texas. Cities aren't designed for public transport. They're designed for you to have a car. But there are improvements in design that can help reduce fuel consumption. As long as when you get a chance to buy a car, you vote with your dollar, you're going to hopefully buy something that's got better fuel economy. Hey, it'll save you money in the long run when you don't have to buy gas all the time. So let's look at some kind of thoughts about the future. What are we going to do as far as energy goes in the future? One of America's major exports is culture. And because of that, people in developed countries all over the world, they want the things that a lot of people in America take for granted. Cell phones, cars, a lot of electrical appliances, and that's going to increase the energy consumption of the entire planet. A lot of this is going to happen in developing countries. And you've got to keep in mind a couple of those countries that are going to end up increasing their energy demand are places like India and China, where they just have a large population. So even bringing the standard of living up to not even the level of what we enjoy here in the United States will require an increase in energy consumption, which means that fossil fuels just aren't going to cut it. Um, so we've got to find some other options. Here's a couple of different thoughts. Um, I'm a proponent of the fact that renewable energy is an extremely wise option. I mean, I think it's a crying shame that here in Texas we don't use solar power. In July and August when we're using most of the electricity to produce air conditioning, we're getting tons of sunlight that could be transformed into electricity. Unfortunately, renewable resources may not be able to produce all of the electricity we need just because there are variables in play. If you have a particularly calm day, you don't have a lot of wind, you're not going to get a lot of power from the wind turbines. If you've got a lot of cloudy days, you're not going to get a lot of power from solar power. But if we start incorporating more and more renewable energy, then we can back it up with fossil fuels so that we dramatically reduce our use of fossil fuels. They'll last longer and will have less of an impact on the environment. There's also the thought that we should start thinking about using more or producing more electricity on a local scale. And the ultimate local scale would be producing electricity at our own homes. So increasing the use of solar panels or solar water heaters or maybe even having neighborhood wind turbines might be a useful thing. Of course, technology continues to try to find other ways to produce electricity. Let's look at those in the next slide. So those of you in sixth period already saw Jose Gomez's presentation on nuclear fusion. In his case, he was talking about cold fusion. That's the ultimate dream of energy science, which is to have a way to produce the massive amounts of energy that are produced by things that perform nuclear fusion, kind of like our sun, which is the source of a lot of energy for our planet. The danger is, or the problem is that when you want to achieve nuclear fusion on the level of the sun, you need extremely high temperatures and probably high pressures as well, which is something that's very difficult to duplicate on the planet. So the dream is cold fusion, which can be done at pretty close to room temperatures. There's also thoughts of creating a bunch of arrays of solar collectors in space that could then transfer that energy back to Earth. And there's even talk of trying to use nanomotors that basically use the movement of molecules to produce electricity, if you could get a large number of these working in unison. These are all technologies that basically I'm telling y'all to go out and make. My talents don't lie in the field of engineering, or if they did, I don't know about it, and so I'm depending on you guys to create this stuff. Good luck with that. Alright, I'll see you guys in class. Have fun with the notes.